We have done some few problems on polarization, and the remaining problems we'll do it now. Okay, one or two problems. So I'm switching off my video and sharing my screen. Yeah, are you able to see the screen? Am I audible to all of you?
Sir.
Yeah. So we did some problems yesterday, previous classes, and now I asked her to do this problem as a homework to find the Brewster angle. Now we will do some more problems from the rest of the topics which I have covered. And the problem 6, you can note down all this. Okay. A plane polarized light of wavelength 6000 angstroms is incident on a thin quartz crystal cut. It's a here you see that they are using here a quartz crystal. Okay, not a calcite. Okay, they are the thin quartz crystal they are using it. And having optic axis parallel to the top of the surface means that if you take any of the, okay, if this is the crystal lattice, if you are taking, the optic axis is on the top of it. So okay, any line parallel to the optic axis is also optic axis. Therefore, if you see it, the uh, light will go and come here out of it. That's what we have seen in the earlier classes also. So it is on the top of the axis. Okay. Now that is top means on the top surface of the axis we have to say it. Now what is asking is to calculate intensity of, okay, they're asking to calculate intensities of E ray and O ray. Okay. If the plane polarization is taking an angle of 30 degrees, not 300, this is 30 degrees. You make it as 30 degrees. Okay. Yeah. Now I'm sharing it 30 degrees. To solve this problem, we have seen in the earlier classes that whenever light falls on a doubly refracting crystal, okay, the crystal will uh, make the incident ray into two parts as two doubly refracting surfaces. Therefore, we know that whenever light falls on a doubly refracting crystal like this, okay, it will be split into two parts. One is E ray. This is E ray having vibrations in the principal section. This is what we call it as E ray. And the ray which is having vibrations perpendicular to this, we call this as O ray. Okay. And they are talking that the incident ray is falling on it at an angle equal to 30 degrees. They have given it 30 degrees. So therefore, we say that you can resolve this is the axis I am taking. Now incident angle is, suppose here the incident one, and I suppose amplitude is A of this. And this is making an angle 30 degrees. Now I have to find out the components, X component and Y component. And this will become A cos 30 degrees. And this will become A cos, okay, A sine 30 degrees. A sine 30 degrees. Okay, these are the two components. The components that are having perpendicular vibrations is O ray, and the component which is having a parallel is called E ray. Therefore, if I represent this will be this component, whatever I'm taking, okay, will be E ray because this is parallel to the axis. And the component which is perpendicular direction, this is the perpendicular direction component, and this component whatever I'm taking on this will be O ray. So they're asking to find out ratios of E ray and O ray. So even the, of course in this calculation we don't require any lambda, but if you want to write the solution of this, I suppose here that, okay, lambda they have given as 6000 Armstrong units. which is nothing but 6,000 into 10 to the power minus 8 centimeters. Okay. Then there are also to calculate intensities of E ray. I call it intensity of E ray, yes, IE. Okay, this is E ray intensity. So before calculating E ray intensity, I'll calculate amplitude, and then if I square it, I will get the value of the intensity. Therefore, I'm writing here E ray amplitude. I want to calculate first E ray amplitude. So E ray amplitude, I am showing it by IE. Okay, or okay, instead of that, I can write A. Okay, amplitude I'm using. Therefore, I'll write it as A. E is the amplitude of it. So I'll write this amplitude means that here I have A cos 30 degrees is this given. So therefore, I write A cos 30 degrees. So A will be not given the length of the vector. So I'll keep it like this and I'll write cos 30. And what is the value of cos 30? Anyone? Cos 30 value.
Root 3 by 2.
Yeah, root 3 by 2. So therefore, I'll write it as root 3 by 2 into A as amplitude of this. Similarly, I calculate amplitude of O-ray also. So here I calculate amplitude of okay, amplitude of O-ray. If I want to calculate amplitude of O-ray, I represent it as 0. So this is the perpendicular component. This is O-ray. Therefore, I'll write A sine 30 degrees. So therefore, I'll write A of sine 30 is how much? Sine 30 degrees. 1
1
by
by
2.
2.
Yes, so it is A by 2. I'll write it as. So therefore, I'll write intensity of E ray. Intensity of E ray. If I want to write E ray, you know that intensity of E ray is nothing but AE square, which gives you IE. So if I square it, I'll get 3 by 3A square by 4. I'll get. Okay, similarly, I'll find out intensity of O-ray. Intensity of O-ray. So intensity of O-ray, I write it as AO square, which is equal to IO. Therefore, I'll write IO is equal to, here I have A square by 4. Square of this, I have to write it as. So if I write like this, okay, and then I now take it as the ratio of is asking to find out the ratio, calculate the intensities of O-ray and E-ray. And of course, if I want to calculate ratio of intensities. Ratio of intensities, I'm calculating, that is IE by I0, I calculate. Okay. So if I calculate IE by I0, we have 3A squared by 4 is this, and it is A squared by 4 as this. If I cancel, I'll get 3 by 1, which is 3:1 ratio. Okay, if they are asking to calculate only the intensities, this is the intensity of E ray and this is the intensity of O ray. If we want to ratios of intensities of E ray, I have to take the ratio. I'll get 3:1 as the ratio of intensities. Okay, and we will do the next problem. Did you complete this? Shall we move to the next problem?
No, sir, 1 minute. Can you
Yeah, yeah.
scroll once up?
What do you want?
The O-ray diagram, sir.
Yeah, this diagram, O-ray diagram. Okay, so you know that O-ray and E-ray are two plane polarized lights of perpendicular vibrations. So we know that O-ray will have vibrations perpendicular to principal section vibrations. Okay, O-ray vibrations are perpendicular to principal section. That's the definition what we have seen principal section. And E-ray, you know that will have vibrations, okay? Vibrations are in the principal section. Vibrations are in the principal section. Means that they are parallel to it, principal section. So I'll suppose now the principal section is along the optic axis, which is along x-axis. This is x and y. Therefore, incident light is now having an amplitude A, which is a light vector, E vector, because polarization is because of the electrical vector or electric component of the electromagnetic wave. Hence, I have taken this incident wave as 30 degrees. This is the vector quantity. This vector quantity can be resolved into horizontal component and vertical component. Then horizontal component will become E ray, vertical will component will become O ray. Hence, I have A cos theta will be E ray, E ray length of the vector, and length of the vector along the y-axis is O ray, whose value is A sin 30 degrees. These are the two components, x and y components. Thereby, I am using here the amplitude of E ray and amplitude of O ray. Did you follow?
Yes, sir.
Yeah. Shall we move to the next problem? Okay. So I'll go for the next problem. Just look at the next problem. It's a very simple problem, but he's asking to find out the incident wavelength they have given. So to find the solution of this, whatever given I am writing, wavelength lambda they have given as 6,000 Armstrong units, okay, which is nothing but 6,000 into 10 to the power minus 8 centimeters. This we know it. Find the thickness. They are asking to find out the thickness T. How much is this? For which plate? Okay, a light wave of incident on a quarter wave plate is said. Okay, so they have given quarter wave plate. Quarter wave plate. So quarter wave plate will introduce. Okay, quarter wave plate will introduce a path difference PD between O ray and E ray equal to lambda by 4. It's a quarter wave plate. So that introduces this value. So therefore, I suppose now to find out thickness T, we have seen the thickness T is lambda by 4 into mu E minus mu naught. So, but we have used it for calcite. Okay, here they are using material whose O ray, that is mu naught, they have given as 1.544, which is smaller than the refractive index of E ray, means that E ray moves faster. Okay, so therefore I have to write here mu E first, because it's a quartz crystal. But previously, okay, this is a calcite crystal. Mu is mu naught minus mu E minus mu naught. If mu naught is less, suppose in the given problem than this, that means the crystal is different from this crystal. Hence, we have to write this one. Therefore, the general formula T, I can write it as lambda by 4 into mu E difference mu naught, depending on whether this is a positive crystal or a negative crystal. Okay, if you take a positive crystal, then like quartz, mu E is more. If you take a negative crystal like calcite, mu E is less. Therefore, here I am taking like this. To find the thickness T, I put lambda value as 6,000 into 10 to the power minus 8 by 4 into mu E is 1.553 minus 1.544. If I subtract it, I'll get the value of the thickness T, which gives you thickness T is equal to, how much are you getting? Can you do and tell me? So if I cancel this, I'll get 30, 15, 15,000. If I cancel 4 on this, okay, 1500, sorry, I'll get 1500, okay, into 10 to the power minus 8 by 4 I have cancelled already is 15 times. And if I want to subtract here, if I want to subtract this 553, 1544, okay. So I'll get here. How much are you getting? This.
0.9, sir.
0.9. Okay, 0. And this is 0. 0.009 or 0.9?
0.009.
So I have to write it as 9 into 10 to the power minus 3. Then simplify it, find the value of T, that is, okay, the value of thickness in centimeters. So how much are you getting T thickness?
0.0016.
0.0016
6.
0016 centimeters.
Yes.
Okay, that means it is 16 10 to the power minus 4 centimeters. Yes.
Yes, sir.
Yeah. This is the thickness. Thickness is very, very small if you say it. Okay. This is the value of the thickness of it. And if you compute this, we'll go for the next problem. Okay. A similar problem. The problem is a light of wavelength 6000 Armstrong is incident on a thin quartz crystal cut plate having optic axis parallel to the top surface. They're asking to evaluate minimum thickness of the crystal plate that introduces a phase difference of 60. Okay. They did not say that whether it's a quad is a half wave plate or quarter wave plate. You know that quarter wave plate introduces lambda by 4 wave path difference between O ray and E ray. If it is a half wave plate, it reduces a path difference of lambda by 2 between O ray and E ray. Now they said it is only 60 degrees between O ray and E ray. So whatever the values they have given, I'll write here, and you can write like this. Solution, if you want to write it as, we have lambda is equal to 600 10 to the power minus 8 centimeters. And they have given O ray and E ray mu 0 is 1.54, and they also given mu E as 1.55. Okay, because O ray is this, E ray is this, respectively, they have given it. Then they're asking quartz they have given and evaluate the minimum thickness. What is the thickness T to introduce, okay, 60 delta phase difference, okay, is equal to 60 degrees. So you try to calculate this delta into path reference lambda. Okay, therefore I write phase difference delta is equal to 2 pi by lambda into path difference. So path difference they have not given, we have to calculate. Therefore, I write path difference, okay, is equal to delta into pi by lambda by 2 pi. This path difference I have taken this is the other side, so I'll get lambda into this. They have given this as 60 degrees into pi by lambda by 2 pi. So we know that if it is 60 degrees, okay, if I take 60 degrees, okay, so this is 3. So I'll get 60 degrees here by 3. So therefore, what I do here is that I'll convert this as I have 2 pi by lambda, and 2 pi is 360 by 3. I'll get you 60 degrees. 2 pi is, okay, 360. 360 by 3, if I take it 2 pi by 3, this goes 3 one time, sorry. Okay, 60 degrees I have to get it as. So therefore I make this by, okay, if you just say it, so they are giving it as 60 degrees. If I take 60 degrees here, 60 I'll take it as, okay, 3 times it will go, and that I have to take into account to calculate this. Therefore, okay, pi by 6 if I take it this one. Okay, I'll just redraw this. Okay, 2 pi by lambda. So I have here 360. So I'll write it as 2 pi. I'll write it as 2 pi. Okay. If I divide this 2 pi is nothing but 360 degrees. I want 60 degrees here only. Therefore, I have to divide this by 6. If I divide by 6, I'll get 60 degrees. Therefore, 60 degrees is nothing by 2 pi by 6 into lambda by 2 pi. So you can cancel 2 pi, and I'll get lambda by 6. Therefore, a phase difference of 60 degrees equal to a path difference of pi by 6. Hence, I will now do it and find it out that, okay, thickness we have is the thin quadruplet 60 degrees. 60 degrees means our formula T will become T is equal to lambda by 6. If it is a quarter wave plate, lambda by 4. If it is a half wave plate, lambda by 2. If it is 60 degrees, lambda by 6. Into we have, as usual, mu naught minus, okay, sorry, mu e minus mu naught. So we'll write this as mu e. Okay, 1 minute. I'll write this as a formula again here. So this is mu e minus mu naught is the thickness, for which I will get lambda is 6000 into 10 to the power minus 8 by 6 into 1.55 minus 1.454. So how much do you get this T value? Roll number 21, can you tell me the answer? Roll number 21, 22,
0.001, sir.
0.001 centimeters, 0.001. Is it correct, all of you? Please check.
Yes, sir.
Correct. Okay. So this is the next.
Yes, sir.
Yeah. So we'll go for the next problem as a homework. You have to do by yourself. Okay. This is a homework. You have to do it. So what is the problem they have given? Lambda they have given. Okay. As usual, as 550 into 10 to the power minus 8 centimeters. Okay. And O ray, E ray refractive indexes they have given. Mu E is equal to 1.654. They have given here mu E is more. Okay, sorry, this is mu O. And mu E they have given as 1.486. And now they want to calculate three different parts. One, what should be the thickness if it is a quarter wave plate? What is the thickness if it is a half wave plate? And what is the thickness if it is lambda by 8 plate? You can use the above formulas to calculate the thickness T for these three different cases. What is T? They're asking to do it. Okay, so as a homework, you do this and find it out. Can you do this? Yeah, roll number 11. Can you do this? Chinmay. Yeah. 54, Swapna. You are absent yesterday. What happened?
Srivar, sir.
56 Tribhulesh.
Sir,
Yeah, you're all absent yesterday.
yes, sir.
Yeah, why? You're so busy. It's okay then. Okay, be regular to the classes, all of you. Now, this is the problem you have to do by yourself to calculate
Yes, sir.
the thicknesses of it. Okay, so I'll close this chapter with these problems. That is, unit 2 is closed. So, in unit 2, we have interference, diffraction, and polarization. So, unit 1 is completed, unit 2 is completed. Now, we'll start unit 3. Okay, so we will go for unit 3. Unit 3 is basically having, okay, this is, we are starting unit 3. In unit 3, we have two parts. Okay, first chapter A is on lasers. You have already done an experiment on lasers. You have seen the laser light. And B, we have optical fibers. Optical fibers. These are very important for your engineering, because in civil engineering, lasers are so much widely used now for measurements, okay, for finding areas, distances, lengths, heights, and quality control also. And optical fibers are used as a communication channels, and they are now used in civil engineering constructions like bridges, etc., as a sensor elements to see and monitor the stability or health of the given bridge or a construction. Therefore, we have optical fibers in, okay, health monitoring systems of the buildings or health monitoring systems of bridges, etc. Hence, we will now find, okay, look into the details of how lasers are produced, what are the principle, what are the different types of lasers and their applications, and construction working of different lasers also we'll see it in the first part. Second part, we will look at optical fibers, their construction working, etc. And you have done these two experiments in our physics lab. So therefore, you'll have a lot of Viva questions from these two chapters, which we are, of course, we are going to cover those question answers in this session. So therefore, I'll start now, okay, here with the chapter lasers. There are two parts of it, okay. We will start with this lasers. So we start with the laser chapter, lasers. Before going to see what is a laser and all other basic things, anyone can you tell me the full form of laser? It is a, okay, acronym or a short form of it. And anyone can you tell me what is the full form of laser?
Light amplification through the
Uh, Light amplification. Yeah, yeah, continue.
simulated emission of radiation.
Emission of radiation.
Radiation.
Okay, so we will now define it is as, okay, simply it is L for light, okay, A for amplification. So this amplification of, okay, light amplification by, not of, by stimulated emission, stimulated emission, E for emission, we'll take it as emission of radiation, I'll take it as radiation. So this is very important one, you have to find it out. L for, okay, light amplification by stimulated emission of radiation is a full form of the acronym laser. So this laser acronym will give you many important ideas about laser. It is what is telling light is amplified. That means the intensity is increased. By what process? By stimulated emission process. What is the stimulated emission process? How to get the stimulated emission process in a given system? We have to say of radiation. Therefore, laser is nothing but just like any other light and a part of electromagnetic spectrum, because electromagnetic spectrum is a spectrum of radiations. We have seen in the earlier class that electromagnetic spectrum consists of several wavelengths and in which visible spectrum is a very small part of it. Therefore, the EM spectrum is a very large spectrum which consists of okay ultraviolet rays, visible okay IR, we have radio waves, microwaves, okay microwaves, and then we have okay many other waves including sky waves and so this is a very huge spectrum, uh, radio waves, okay radar wave or microwaves, etc. Of course x-rays also may be in this, etc. we have made. So therefore the laser is like just like light, it is electromagnetic radiation only. So, but it has specific characteristics when compared to ordinary light. So, therefore, we will see before going to see the details of laser, how we are getting and all that, we first write characteristics of laser light. Okay. Well, we'll compare the characteristics of laser light with the ordinary light, and thereby we know the differences between ordinary light and the laser light. Characteristics of the laser light. You should remember that it is just like any other light. Okay, it's a part of electromagnetic spectrum. So it also will have different wavelengths and you can see different colors also. That means lasers may be in green color, blue color, red color, okay, green color, etc. That will happen. And lambdas, whatever the green color lambda is there, that is also there for laser. Don't say that laser will have different lambdas for different colors. But what important characteristics of laser light are, okay, we have to look at the important characteristics of laser light. So some of you have already known the important characteristics of laser light, which we have seen in the lab classes. So can anyone tell me what is the important characteristics or properties of laser light? Anyone?
Sir, it is monochromatic.
Very good. So we start the monochromatic. Later you can tell remaining. Monochromatic. Monochromatic. We say that the light is laser is highly monochromatic. Monochromatic means single frequency. Therefore, laser light contains okay single frequency or single wavelength, we call it as mono means single wavelength. So laser is hence it is, we say, highly monochromatic. Highly monochromatic. But how monochromatic, how much it is, we have to say it. Mono means, if you see, okay, mono is single, okay, or one, we say single. And chroma means color. Chroma means, this is chroma means color. We say color. So single color, single wavelength will be there. So therefore, for any laser light, if I say monochromatic, means that there must be single wavelength. But in general, that is not possible, even though, okay, you can take approximately maximum in cases laser as monochromatic light, but the line width is very important for any laser. Line width is nothing but we have to find out how many wavelengths that are emitted by the laser light within that. Suppose say it is 600 red light, 6000 Armstrong's light you are taking, red laser I am taking it. So this 6000 laser light will have a peak, goes up to this maximum and comes here and falls like this. Therefore, okay, this peak value, if I take it, this is actually peak corresponds to, if it is a red color, then it is 6000 for red. Okay, we say red. And if I draw here, okay, anything, this is the, I'm taking on this, of course, lambdas. This is 6000 lambda I'm taking. Armstrongs we are taking. And how many other frequencies are also there, we have to see. This is actually called as line width. Okay, but for lasers, they are very, very narrow. But if you take a LED and other bulbs, they are very, very large. So therefore, if you take, this is for laser. Okay, laser is very, having, okay, narrow line width. They will have narrow line width. So laser will have narrow line width, therefore only one or two very small. If at all there are any other frequencies also in this peak value, they may be approximately delta lambda is maybe around very, very small, maybe approximately 50 nanometers or so, or less than that also, 50 nanometers. Very, very small, if at all, a typical value. But if you take a white light source, okay, then this will be, if I take lambda on this, then it will have a very big and, okay, very big and something like this. It's not narrow. Therefore, in this, if you take it, we have different colors, okay, starting from here I have maybe violet will be there here, and on the other, suppose say here I have red. Okay, this is red lambda, this is lambda for violet, this is lambda for R. So therefore the white light spectrum consists of many colors. This is I say here is lambda green, and in between we have all VIBG or colors. That means there are many wavelengths are there in it, whereas in uh, lasers, the line width is very, very short. And in some cases, okay, the line width is absurd that, okay, if I take lambda here, if this is the peak value, it is observed that single frequency is also possible. Thereby, we have a very, very short falling like this, very short value like this is falling. Okay. That will be there. So this is called monochromatic, means single wavelength. So the second property I look into this, the first property is monochromatic. Therefore, we'll write here that, okay, the lasers are highly monochromatic. This is the first property. Okay. The second property of any laser light, yeah. Anybody can you tell the second property of laser light? Yeah. What
Coherent
is it?
light source.
Hmm? Coherent light source, correct.
Coherent.
Yeah, yeah, coherence. Coherent. So therefore, coherent. Okay. Laser light is highly coherent. Highly coherent means that they maintain the same phase difference. All the, okay, maintain same phase difference. Phase difference. Highly coherent. So therefore, if I take a laser light like this, okay, if this is the laser light is going like this, okay, then the next wave is also again same. Wherever we have maxima or we say crust and trough, we also have same crust and trough, and they maintain the same thing just like this, and they'll come. And if I take one more wave also, exactly they go like this. Okay, exactly they go like this. They maintain the same, okay, uh, phase difference at any point, and thereby I'll get like this. So okay, I have not written up to this. I'm writing it again. Okay, so thereby you can say that any point if you select it, this point or this point or this point or this point, the phase is same for all the waves. Phase is same. We call such lights are coherent lights. But if you take incoherent, okay, they don't maintain the path difference. That means one wave may be like this, the other wave if you take it of the same source, okay, it may go something like this, or other wave may go something like this, and maybe if you take different wave, that wave may go like this. So therefore, they don't maintain, okay, do not maintain phase, any phase relation. This is what we call it as coherent and non-coherent beams. We want coherent beams for many applications like spectroscopic application and also to get interference. So any two different laser sources can also be treated as coherent sources for many practical applications. And we will now look at the third property of laser. Anyone, can you tell me third property?
Sir,
Hmm.
it's harmful.
Yeah,
I don't
harmful.
know if that's a property, but you can't focus laser
No. So that is
directly.
we call it as okay, dangers or okay for looking the laser light directly.
Okay.
That we'll see. But exactly we have some more important properties is that okay, because they're coherent, there if I take interference of this, all crust and trough are falling at the same time, therefore they undergo constructive interference, hence intensity increases. Hence therefore we say that lasers, okay, we'll now write it here as for high intensity, very high intensity. That's why you cannot see with your eyes. If you see with your eyes, this high intensity will burn and harm your eyes. Those are called hazards of lasers, high intensity. Laser beam is very narrow, okay, narrow focusing and coherent and coherent. Hence, the intensity here, if you see incoherent beam, if you see this, their crusts and troughs are not falling. Therefore, they can some of them will cancel each other. Therefore, net intensity is very less. So therefore, okay, beam is very narrow and coherent. Hence, intensity of laser light is very high. So that means if you take here, suppose a laser light, something like this, which are highly coherent. This is a one, this is the coherency I am taking. This is also highly coherent waves I am taking. And this may be also very coherent waves I am taking. Then if I want to draw the resultant one, all these add together, and therefore the resultant one, if I want to write, the resultant intensity will go up maximum and go here and goes maximum here. Therefore, very high intensity. Because of high intensity, it gives you a lot of energy focus in a small area, and hence it is dangerous to see for us, for with our eye, and our eye will be get damaged. If you take, suppose, say one wave is something like this, other wave is some going like this, and one more wave is going like this, then there is no phase relation, and resultant will be, okay, so here something falls here, and it is not that one. So intensity is not added up. Here intensity is added up, and we have higher intensity. So coherency or monochromatic, coherent, high intensity, and anyone, can you tell me the next property of laser?
It travels in a particular focus direction.
It can be focused, means high focusing action. So because of this high focusing action, I write this as, okay, the beam is less dispersive, or we say it is narrow and concentrated. Okay, so less divergence or no divergence, you can say less divergence. The laser beam is focused to a narrow a laser beam is focused to a narrow place, and okay, or instead of that, a laser, I write it as, is focused, okay, laser is focused to a narrow beam, and it will not disperse not disperse much and concentrated into small area. So this is the fourth point. What do you mean by this fourth point is that if I say the laser beam is focused, and means that if I take any ordinary bulb, so I take a bulb, ordinary bulb, a filament bulb I am taking. So the light coming from this filament bulb, if I take it, so one of the ray goes like this, other ray goes like this, other goes like this, and goes like this. The spread is large. Spread is large. Even if you take sun, or if you take any other lamp like a tube light, or if you take a sodium vapor lamp or mercury vapor lamp, they are not coherent sources. Okay, they are incoherent sources. So therefore, light spreads. If you switch on a bulb or a tube, the light coming from the entire tube will be spread in the given room, and it is not concentrated. Because it is not concentrated, the occupied area is very large, therefore intensity is less. But if I take a laser beam, okay, a laser, I'll take a laser here, a pointer, laser pointer. You know, you might have seen the laser pointers when you are playing at your houses with laser. It is a dot focused, and thereby this will not focus, but however, okay, it just goes from this point, and it will be going away just like this. Okay, so thereby you can say that this is simply, okay, goes straight away from, okay, straight away from the point of focus, or from where it is emitted. So the laser beam may be something like this, okay, or you can say this may be so. Okay, if I take it, I'm sorry, I'll just do it again. Shape of this I'm writing here. This is one, arrow, and we may having another arrow something like this, another arrow like this. Okay, they don't spread. So this angular spread, because you see it is started from here, angular spread is very large, but if you take this ones, the angular spread is very less. It goes as a spot for very long distance, and angular spread, or angular dispersion we call it as, angular spread is very low. So therefore, it is highly convergent. Highly, so it will not disperse, just like ordinary lamp. It's a ordinary light. Ordinary lamp or ordinary lamp, if you take it, the light disperses. So dispersion is large. Dispersion is more. That's why spread is more. But here, angular spread is very less, as they go straight away from the point of source of the laser to long distances. Because it is not spreading, you can use it for the length measurements and also to concentrate energy at a particular place. That is the advantage of these lasers. So these are some of the important properties of laser. In addition to this, you may have other properties also for lasers. So these are the properties of lasers. The properties of lasers, if you say one, I write here as, okay, first important thing, they should be monochromatic, okay, single wavelength, monochromatic, and we have coherent. They show coherency, highly coherent, and they are less dispersion, or we say low dispersion, and we also added the third one also as high intensity. These are the important characteristics or property of laser lights. These are the laser light properties. Laser light properties. Okay. Now, but how do I get laser? Why it is so special when compared to ordinary light? Why ordinary light is spreading like anything? Okay, and what is the phenomena by which laser light is produced? To understand the production of laser light, you should understand three important transitions, and these transitions are very important, okay, to. So therefore we now look at three different processes, okay, of electromagnetic radiation. So thereby we have when an EM wave means electromagnetic wave, maybe ordinary light or maybe laser. Okay, when an EM wave interacts, means if it is incident on falls or absorbed by the substance, okay, when an EM wave interacts with, okay, when it's solid or material, we say that, okay, when it is material, interacts with material, with the material, we have we have three types or kinds, okay, of interactions with, okay, those three kinds of interactions or three kinds of processes occur. Kinds of processes will occur. So we have to look in the next class what are these processes and how they went. So I list the processes, but in the next class we'll see in detail about this. First process is called induced absorption. Induced absorption, or simply it is also called as absorption. Okay, and the third one, we take it, the second one, sorry, second one is called spontaneous emission. Because spontaneous emission, so this is emission, first is absorption. Okay, and I take the third one as, which is important and is a principle for lasing action or to produce laser, is called stimulated emission. First two are known to anybody for a long time, but stimulated emission is a new one which was actually proposed by Einstein, and that's why this is initially not known, but it is produced by introduced and given a concept of stimulated emission, and thereby the emission of coherent beam called lasers, and it is given by Einstein. So Einstein proposed this stimulated emission, and thereby we have Einstein coefficients also in it, but we'll see it Einstein's proposition thesis. So now in the next class, we will discuss these three and also reasons for lasing action and how lasers are produced and what are the basic requirements for any laser. Okay, so this is the what we have learned in this class. So I stop here, and you can see in the next class the details of this. Okay, so if you have any doubts, meanwhile, you please ask and clarify from this topic.